In this lecture, we're going to review a little bit about acid strength and then how we use numerical values to compare the strength of an acid. And finally, we're going to kind of culminate in how we don't even need those to, if we just wanted to do a relative comparison of the strength of a series of acids, how we could just look at the structure, not even know what the pKa values are, and be able to rank compounds by their acidity without needing pKa values. So just to review, in an acid-base equilibrium, the way we could determine the strength of an acid is by looking at how much or what degree does that acid dissociate? To what degree does it donate that proton? And so we basically would calculate, you did this in GChem, calculate the equilibrium constant. In this case, we called it Ka. The acid dissociation constant was products over reactants. So the concentration of the products over the concentration of the reactants. And then we didn't need to include water. If water was a reactant, we never include it in the equilibrium constant. Now that tend to give us very, 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 very large numbers with like large exponents, or very, very, very small numbers with like negative exponents. And those were kind of a pain to deal with. So one of the things that we did is we would take the negative log of that Ka to get pKa. And those gave us like numbers that were a little bit more reasonable to deal with. But it's important that you remember the trend from general chemistry. Strong acids have small pKa values. Weak acids have large pKa values. pKa and Ka is an inverse relationship. If Ka is big, that means it's a product favored equilibrium. That means pKa is going to be very small. Or I don't say very small, but small. Now, to put your mind at ease, because I know you're looking at this already, oh, great, I got to remember how to do ice tables and all this stuff. We don't do those kind of calculations in OChem. I'm assuming because you passed GChem, you've mastered, how to find an equilibrium constant. You do need to know what these numbers represent, though. And so if I were to give you pKa values, you should be able to rank various acids, either rank them in terms of acidity or even basicity. Now, this table here, I do not expect you to memorize. I don't want you to memorize it. I do kind of want you to look at some of the trends, though. Okay. At the bottom here, we have a lot of our inorganic acids that you're kind of familiar with. Notice we call all of those strong acids. They have very low Ka values. I'm sorry, pKa. And then as we kind of go up, we're getting more into organic acids. And then we include things up here like ethane and ethylene. These are never acids. Their pKa's are so high. Like there isn't a base that exists that's strong enough to deprotonate those. But again, I want to highlight some important things from general chemistry. And one of those trends is the inverse relationship between the strength of an acid and the strength of its conjugate base. So the weaker the acid, the stronger the conjugate base, and vice versa. The stronger the acid, the weaker its conjugate base. That's an important trend you learned in general chemistry, and I do want you to remember that from remember that going into organic chemistry as well. Now, what do we do with these numbers? Well, in general chemistry, you use them to predict the position of an equilibrium. So if you have an acid-base equilibrium, so if it's not a strong acid, there's going to be an equilibrium that favors one side or the other. We would use those pKa's to determine what position the equilibrium lies in. And the rule of thumb is, well, first of all, identify your acids on both sides. So you have acid on the left, conjugate acid on the right, and you would look at the pKa values of those. The equilibrium lies away from the stronger acid, which kind of makes sense. The stronger acid is the one that wants to dissociate more. And so this equilibrium is product favored because acetic acid has a lower pKa. Let's look at another reaction. So here we have a compound known as phenol, and we react that with bicarbonate. This is our acid. This is our base. And that forms something we call the phenoxide ion and carbonic acid. So this is our conjugate base and conjugate acid. Now the pKa of phenol is about 9.95. I don't want you to memorize that. We're just looking at numbers here. And the pKa of carbonic acid is 6.36. So all we have to do is compare the numbers. The equilibrium will lie away from the stronger acid. Well, since carbonic acid is the stronger acid, this is a reactant favored equilibrium. Now, again, that should mostly be review from general chemistry because you used pKa values um, and did some comparisons. But what happens if you don't have the pKa values? So in this acid-base equilibrium, what direction does it lie? They say, well, that's not fair. Where's the pKa values? Can I look them up? And I'm going to tell you, you can solve this without pKa values. The key thing here is that the stronger acid can be identified by figuring out which base is more stable. You're going to find the base on both sides and ask yourself, what is more stable? So of these bases here, not those two, which is more stable? The more stable ion comes from the stronger acid. And that kind of makes sense because again, we're talking about stability here. The reaction wants to proceed in the direction that leads to the more stable product. So the more stable ion is going to come from the acid that wants to deprotonate more. So we are going to look at taking an acid, reacting it with a base, and looking at the resulting ion. And ask ourselves, which one is more stable? Now, how do I do that? How do I look at a base and figure out its stability or look at the relative stability? We're going to use this acronym REO. Okay, so just kind of memorize that acronym as well as the order. because it's arranged in the order of importance. We always start with A, see if there's a difference. If not, then we go to R, see if there's a difference, and then go to I, and then O. Now there will be some exceptions to this, and I'm going to do, a couple examples where an exception applies, and it's few and far between. So what does the A stand for? The A in ARIO stands for atom, and it depends on if you're comparing atoms in the same row or the same column. If you're comparing atoms in the same row, the more electronegative the atom, the more stable the ion. So let's look at these three acids here: methanol, methylamine, and ethane. In each case, we're getting rid, or this is donating one of these protons here. And so we're going to look at how stable is the ion that results. Well, we're just going to compare the atom with the charge. In this case here, that's oxygen. Here, that's nitrogen. And here, that's carbon. Now, since those are in the same row, they're both in the second row. Oxygen is more electronegative. And so notice how its pKa is lower than the other two compounds, indicating it's a stronger acid. Because once the hydrogen leaves, having the negative charge on an oxygen is more stable than having it on nitrogen or carbon. Now, what if we're going to compare in the same column? In the same column, the larger the atom, the more stable the anion. So this kind of goes back to the example I showed a couple pages ago. And I'm going to just delete these here, pretend those aren't there. And I'm going to ask you, what direction does the equilibrium lie? Okay, well, this is the acid on the left. This is the conjugate acid on the right. This is our base on the left. This is the conjugate base on the right. And we need to ask ourselves, which of these two is more stable? Well, if we look at a periodic table, oxygen and sulfur are in the same column. Oxygen is higher than sulfur, so it kind of goes like this: oxygen, sulfur. And remember that atomic size and ionic size increase as you go down a column. Size increases. Now, the bigger the atom, the more it can accommodate electrons, allows them to spread out more. So if something has additional electrons and it's a very large atom, like sulfur, it can accommodate those extra electrons better than oxygen can. So this S minus ion is more stable because it's bigger. The more stable ion comes from the stronger acid. We didn't even need any pKa numbers, and in fact, I'll bring them back now. If you look at the pKa values, notice for methane thiol, the pKa is lower than methanol. That means this is a product favored equilibrium. We didn't even need the pKa values. All we had to do is look at which base is more stable. Now, the last thing about the atom is if you're comparing the same atom, so that means there's no difference in electronegativity and there's no difference in size because it's the same atom, but one has an extra hydrogen and it's positively charged, that one's more acidic. Let's compare water. to hydronium. Notice hydronium has an extra hydrogen and it's positively charged. The pKa of hydronium is negative 1.74. That's pretty acidic. The pKa of water is 14. Not so much. Let's get a little bit more organic in nature here. So let's look at this amine compared to this one. So notice the one on the right has an extra hydrogen and a positive charge. The pKa for this compound is 4.63. Compared to the one on the left, the pKa is about 30. So really when you are comparing the atom, and again, you always start at the atom first. If they're different, look and see if they're in the same row. If not, look and see if they're in the same column. If they're the same atom, then most likely there's a difference in the number of hydrogens and the charge. Now let's look at the R in ARIO. The R stands for resonance, specifically resonance stabilization. There's that term again. We've already seen it come up quite a bit in this chapter. And we use resonance. So if we can't figure out any difference in the atom, then we go to resonance. So for example, we're going to compare this alcohol to this carboxylic acid. And kind of ask ourselves which one's more acidic. Well, if we get rid of the proton, so we add some sort of base, and let's practice doing a mechanism here. So we use a base to pull off a hydrogen. Let's do that here. And let's draw the result of that. So for the alcohol, we get that anion. For the carboxylic acid, we get that anion. Now, the A is not going to help us here. The A in ARIO won't help us because the charge is on oxygen in both cases. So then I go to R. Can either of these compounds exhibit resonance? Well, for the alcohol, there's no resonance. That charge is stuck on the oxygen. Why can't I move it to the carbon here like this? Think about that. That carbon's sp3 hybridized. Remember, one of the golden rules of resonance, you cannot move electrons towards an sp3 hybridized atom. But the bottom one, the carboxylic acid, once it's deprotonated, I can move that negative charge to another atom. Resonance, stabilization. So if I were to ask you based on that, which ion is more stable? We'd say this one. The more stable ion comes from the stronger acid. So this acid or this compound is a stronger acid than the alcohol. Now, if I can't decide by the atom and maybe none of them have resonance or they have an equal amount of resonance stabilization, what do I look for next? Next one I look at is the inductive effect. This is kind of similar to resonance in that the end result is the same of spreading a charge across multiple atoms. I don't use resonance arrows to describe the inductive effect. I use electronegativity. So the acidity will increase if there's an atom nearby that is very electronegative. So let me show you an example here. So here we have acetic acid. pK of acetic acid is 4.76. Don't memorize that. That's not the goal. Using this to compare. If I put a highly electronegative atom close to this acidic proton, like a chlorine, okay, what happens to the pKa? It goes down a lot. If I put another one on, it goes down even more. And then if I replace all those hydrogens with chlorines, now we're kind of getting in almost like strong acid territory. So why does putting a highly electronegative atom there increase the acidity? Well, somehow it's got to stabilize the anion. So let's compare the anion for this acid. So again, I'm just deprotonating to this one. Now they both have the same atom. Both of them have the same resonance. So the difference here has to be the chlorine. Now, chlorine is a very electronegative element. So as soon as it sees that negative charge, it's going to start pulling those electrons towards the chlorine, and you get this partial negative side over here. So not only is the negative on the oxygen, it's also partially negative on the chlorine. You're spreading out that charge. Notice I'm not using curved arrows because it's not resonance. But having that chlorine there spreads that negative charge out. And if I make it even, to the extreme and look at 3 chlorines, now I got a lot of partial negative over on that side. So the inductive effect is stabilizing the ion through electronegativity. I do want to highlight the effect decreases farther away the atom is. So this is a stronger acid than this because that chlorine is farther away. And pretty much after any farther than that, the effect is almost zero. So let's look at a practice problem before we move on. I'm just going to name these A, B, C, and D. What I would like you to do, maybe put the video on pause after I tell you here. I want you to rank these from least acidic to most acidic. So let's kind of start on the opposite end of that. Let's start with the most acidic one. So we're looking for electronegative atoms close to the acidic hydrogen. So both B and C have highly electronegative atoms the closest. What's the difference though? One's fluorine, one's chlorine. Which atom's more electronegative? Well, fluorine's more the most electronegative atom on the periodic table. So the inductive effect is going to be greater for fluorine than it is chlorine. So C is going to be the most acidic. And then close behind that will be B. Now, why didn't I pick A to go after C? Because that fluorine is farther away. So A will come next, and then finally D. Now, the last part of the ARIO acronym is O, which stands for orbital. When all else fails, the acidity increases with more S character. Now, if you look at an sp hybridized atom, sp is 50% S and 50% P. sp2 is 33% S and 67% P. And then sp3 is 25% S, 75% P. Now, the more S character it is, the better it can accommodate a negative charge. So I want you to look at the comparison here between an sp hybridized carbon an sp2 and an sp3 hybridized carbon. So when that charge is on an sp hybridized atom, it's more acidic than if it were on an sp2 or sp3. And again, just to highlight, we wouldn't even consider the alkene or alkane to be acids at all. There isn't a base strong enough that exists to deprotonate that. But, and we will spend a little bit of time on this in another chapter. Um, a hydrogen on an sp hybridized carbon is slightly acidic. You need a pretty strong acid, but it is capable of being deprotonated.